Okay, so we will continue discussing the convergent divergent nozzle. So, what we had seen the other day is we have a convergent divergent nozzle, the area ratio A exit by A throat will decide everything that is happening in the divergent section once the flow is chopped. So, this would also be your A star if Mach number at throat equals 1. Okay. And what we had seen the other day is if my back pressure P0, if my back pressure is same as my stagnation pressure, there is no flow. So, I would have a straight line here. Back pressure is same as my P0. If I reduce my back pressure a little bit, there would be some change in the flow pattern. So, there will be a subsonic flow. If you reduce it still further, then you would get at some value of back pressure, you would get your throat value, Mach number at throat will be equal to 1, and this we know has two solutions, again depending on your back pressure. So, what I have done here is I have reduced my back pressure, keeping P0 constant and my AE by A throat also constant. So, we are doing this experiment on a given converging diverging nozzle. So, when this is equal to 0, no flow. When Pb is reduced to some value where my throat value, throat pressure, throat Mach number is 1. So, if I reduce Pb to some value such that your Pb equals P exit, which is I call it as P critical 1. So, once I reach P critical 1, I will have a subsonic flow at exit with Mach number at throat equals 1. So, there is in between these two values I have infinite cases which are all isentropic solutions. Between this I have infinite isentropic solution, meaning I can have any value between Pb and Pc, P critical 1, and all those solution would be isentropic solution, but the Mach number at throat will not be equal to 1. Now, if I reduce this further, I will have some value. Okay. I do not know what this situation is, I will try to explain that, but I continue decreasing my Pb, it would reach a condition P critical 3, which would give me a supersonic flow or supersonic Mach number at the exit with obviously my Mach at the throat is 1. So, if I keep reducing my back pressure till it reaches P critical, I have again infinite number of solution, but they are all non-isentropic. So, any solution between any pressure, back pressure between Pc1, P critical 1 and P critical 3 are non-isentropic. Okay. So, I have used critical 3. So, there is somewhere in between there is P critical 2, which I will explain it in a while. Now, if I reduce my back pressure further down, so I would draw that here. So, I would reduce P critical. So, my back pressure here is less than P critical 3. I have a situation here, my P exit is greater than P back pressure. So, every condition in between P critical 1 and my P critical 3, I have here back pressure greater than P critical 3. So, if these scenarios may be something which we will deal it later. So, I can have a shock inside inside the diverging section, which would give me a subsonic flow at the exit. So, so all these values would have subsonic flow at the exit. So, what happens here is for some pressure Pb, which is now greater than P critical 3. So, your P exit is now greater than your Pb. So, I would have a shock here. So, my P exit is here. So, this shock which we will explain what is a shock in a later class. So, it just means that this is a non-isentropic process. So, any value between Pb lying between P critical 1 and P critical 3 will produce a non-isentropic process, which for the time being it is simply a shock. Okay. We will explain what is a shock and how do you find the properties across the shock in a later class. Okay. So, in such cases when your P exit, so if I look at here for this scenario, pressure that goes and then you have the P critical 1, then you have critical 3. Now, here the back pressure is somewhere between these two values. So, your back pressure is here. So, my Pb is somewhere here. Okay. So, my flow should have expanded up to this, but it expanded more than that. Okay. So, if I write it in words, for example, here your P exit is less than P critical 3. Okay. So, let us write about this case. Let us take case A. Case A. The flow should have expanded up to Pb, which is now much less than P critical 3. So, the flow should have expanded up to your Pb, but it expanded only up to P exit, meaning your P exit is greater than your Pb. Okay. So, your flow should have expanded up to this particular pressure, but it expanded only up to this. Okay. Such cases are called your under expanded nozzle or flow condition. Okay. So, the flow should have expanded up to Pb, but it expanded only up to Pe, which is your P exit, that is your under expansion. Now, likewise for my case B, which is your P exit is above this, So, the flow should have expanded only up to Pb. Okay. So, the flow should have only expanded up to this point, but now it has expanded up to Pe. Okay. So, in this regime you have your over expanded flow and this is your under expanded flow. Remember the way we call it, this is under expanded because the flow should have expanded up to Pb, but it expanded only up to Pe. The other way, the flow should have expanded only up to Pb, but now it has expanded to Pe. Okay. So, that this is over expansion. And this is under expansion. This nomenclature has always created problems in the students identifying which case is what, but remember these statements. Okay. So, if you remember this statement, you would it would be very clear. So, the nozzle, if the back pressure is much lower than this, if the back pressure is much lower than this, then your flow is under expanded. If it is slightly higher, then it is this. So, if you consider a rocket nozzle, before that, if this is under expansion and this is over expansion, the region where Pe is exactly equal to Pb is our design condition. So, this particular nozzle with this particular area ratio is designed to work at this particular back pressure. Okay. Any back pressure other than this is either under expansion or over expansion. The purpose of CD nozzle is to have supersonic flow. So, if you want supersonic flow, the area, the throat Mach number should be 1, the flow should be chalked. Once you have reached that, it depends on the back pressure, what is the Mach number at the exit. If the back pressure is anything other than your P exit, it is either under expansion or over expansion. So, if I have a nozzle, if I have a rocket nozzle, so I have designed this nozzle, which means my A exit by A throat is fixed. I am not changing the area ratio, and I am also assuming my P0 is fixed or constant, but this is moving up the atmosphere, which means your Pb is getting reduced when height increases. This is precisely what we have done here. So, we have the constant P0 and constant area ratio, and as it moves up in the atmosphere, your Pb get reduced. Okay. Now, assuming that throat condition happens at the chalk condition happens at the throat, the Mach number is 1 at the throat. I have a solution here. Now, your Pb will decide whether the flow is under expansion or over expansion. So, this nozzle will work for one back pressure in his trajectory. Okay. So, the nozzle is going from Z level to some height, say let us take just 30 kilometer, we will worry about just this height. So, somewhere in this height your PB is equal to P exit, that is the only design condition that is available for this nozzle. All other condition it would be either under expansion or over expansion. So, near the sea level back pressure is quite large. So, it is over expanded here. Okay, your back pressure is much larger than your P exit, that is what it is here. Your back pressure is much larger than your P exit. As it moves up in the air, it goes from under expansion to over expansion to your under expansion. Okay, everything depends on your PB. Okay, so at some particular height you will have the design condition. Okay, we will talk about what will happen to the flow structure, everything after discussing the shock and supersonic jets. Okay, so for the time being, let us just stick to this. Okay, so this is the difference when you are changing your PB, when I keep my P0 and area ratio constant. Okay.